Hello, everyone. Uh, my talk will be on optimization methods and applications, mostly in machine learning or data science, whatever you can call. Uh, yeah, so I'm currently, as Professor Buddhadev said, I'm currently assistant professor in IIIT Hyderabad. Um, and this is more or less also my recent research interest. I usually use optimization methods in variety of computer science domains, including, let us say, computer vision, deep learning, and so on. Okay, so this is the list of topics that I'm going to cover. The main workhorse of optimization methods in data sciences is gradient descent method, so-called gradient descent method. So my goal will be to very thoroughly explain this method, which it turns out to be a very simple method. But there are variations of this method, we will see, and we will get up to a point where I will also discuss a little bit of research problems. So we will see gradient descent method, the very basic thing, and then we will see stochastic variant of the gradient descent method. So this will be a stochastic gradient method, which is actually the method used in machine learning. And as an application, I will show you optimization method in a recommender system. So recommender system is an area of machine learning where you want to recommend certain items. Okay. And last, I will talk about research problems in optimization methods. So all this talk is for the total for all the both the talks that I'm going to give. So I will see where I have to stop in the first part and then the second part. Okay, we will see according to the speed with which we will proceed. So let us, without wasting time, let us go and understand what is a gradient descent method. Okay, so the first question itself is, what is this gradient and why are we interested in gradient? Okay, so from calculus, we know that gradients of a function points in the direction of the increase of the function. Okay, so gradients always points in the direction of the increase of the function. So if I have a function like this, and if I have a gradient like this, okay, so if I take a derivative, basically, this is a function from real value to real value. Then if I take a gradient, and then this will be f prime x, which is taken as at this point x. So I took the derivative of f at x and to the gradient, then this points in the instantaneous increase direction, right? So this is the instantaneous increase of the function, right? So this is f prime x is let me decrease the size. So instantaneous instant increase direction. This is the instantaneous increase direction of the function. So basically it's saying that from here, if I go in this direction, then the function is instantaneously going to increase. So that's why we are interested in gradient. So if you go to higher dimension, so if in a higher dimension, meaning if I go from Rn instead of R1, so Rn to R, then the derivative is of this will be it will be called gradient, right? So then we talk about gradient. So this will be a vector of length n, a vector of length n, right? So so this is something we take from calculus, that gradient points in the direction of the increase. Okay, and so this is the fact that we know from calculus. So if I go in the direction, the negative direction, then it will be the direction of the decrease, let us say, right? So because if this is increasing, then instantaneously this will give us the decreasing direction, right? So if I want to decrease the function value, which is what we do in optimization method, we want to solve problems like minimize function f of x over x. So I want to know where the function is going to decrease, right? So this is why, and we need something to tell us which direction I should go to decrease the function value, and that is the gradient here that tells you which direction you should go to decrease. So this is the direction of increase. If I go negative, then it will be the direction of decrease. So hence, we will go to minus grad f, which gives us the direction of descent. Descent is also called decrease, right? So hence, it helps in pointing to local minima. Okay, so if because as such I don't know where is the minima, right? So I have to start somewhere. Okay, so I will start somewhere. Let us say I start somewhere here. Okay, so here, and then I will take the gradient, right? So I want to go to the minima, right? So if I take a gradient, then gradient will point like this. So that's the direction of increase. Gradient will be a direction on the domain, which is here, and it says that if I move there, then it will increase. So preferably I will go this direction, which in the domain will be this direction. So this will be negative grad f. Okay, so you start from certain point and you go in the negative direction, and then you start you land at somewhere, and then you again take the gradient, and then take the gradient, and then finally you arrive at a minima. So the idea behind gradient descent is now kind of simple. You follow the negative of the gradient of f, because positive of the gradient of f gives you increase, and your goal is not to find the maxima. Rather, let us say your goal is to find minima. So you go to the negative grad f, and then you keep doing this step by step, and you will arrive at the required point. And it helps in pointing to the local minima. So it will give you local minima, because at point this you will be stuck here. Okay, because once you reach the minima, your gradient will be 0, right? So your gradient will be 0 because the tangent will be flat. So meaning the gradient will be 0. And after that, there is nothing for you to tell, because if it's 0, you don't know whether it's increasing or decreasing. Basically, you stay there. Okay. So here, if you see in the picture, these are called level curves. So I will tell you what are level curves. But level curves are useful for the analysis. Useful for analysis of gradient methods. Why it is useful? Because if I have a high dimensional function, let us say in this case 3D, then sometimes it's hard to visualize. Let us say I have a 4D function, right? For 4D function, I cannot even draw. So in that case, I want to project it to some smaller dimension where I can do some visualization. At least in the 3D case, this makes sense, where the function values, I draw the level curves basically. So level curves will be, in this case, these guys are the level curves. So from level curves, I can say that, okay, minima or maxima is somewhere here in the middle of the concentric circles, okay, and so on. So I will define level curve now. So first question is, what is level curve? Okay, and let's see. So level curve of a scalar valued function. So this takes a scalar output. It's a multivariable but scalar output, is defined as set of all xy such that fxy is t. Let us say if its n is 2, then in that case f goes from R2 to R. Then the points are x comma y. Let us say the coordinates, right? So it says for a given t, so this is fixed for us. The given t, collect all those points in the domain xy such that fxy is equal to the t. Okay. So for example, let us practice this with a quiz here. So let us say I want to find a level curve of this function. Fx square is x square plus y square. Okay. So this function is from R2 to R, right? And if I have to compute this level curve, so let us say f0, right? So f0 will be, I write this, right? So set of all x comma y such that fx comma y is equal to 0, right? So basically I have to collect all xy such that fxy attains 0. So what are the x and y values for this 0? Well, there are 0, 0, right? So this set is just 0, 0 point, satisfies this. Similarly, I can go ahead and do f1. So f1 will be set of all x comma y such that fx comma y is 1, right? So in this case, this will be set of all xy such that x square plus y square is 1. So this is a set of all x comma y such that x square plus y square is 1. Now this is a circle with radius 1, right? So this is a circle with a circle centered at origin with radius 1, circle with radius 1, origin is 0 0. Okay, I mean not I mean center is origin, right? So center of the circle is origin, which is 0 0, right? So we all know this. So so level curves of this, right? For t equals 0 is just single point 0 0. T equals to 1 is circles, and so on. With if I take t equal to 2, then circle with radius square root 2, and so on. So if I visualize this, this is a paraboloid. Okay, so this is a paraboloid. How does a paraboloid look like? Paraboloid looks like this. Okay, so we have this two-dimensional thing, space, I mean domain, and so this is the domain of the function, right? So this is the domain of the function, and level curves are basically you fix the height, right? So it says height. So let us say this coordinate is there, which is the t. So I fix t to be 1. Let us say t to be 1. Then all x, y in the domain for which fxy takes the 1 value. So this will be basically this. This is the fxy equals to 1 value, right? So fx comma y equals to 1 value. So what are all those points? Well, those points in the domain are basically these points for which these are the xy, which is in this case it happens to be a circle with center at origin radius 1, for which this height of 1 is assumed, right? So this way I can have level curves, right? So if for this height, let us say if t is let us say half or something, then level curve will be this, and if t is 3 or something, then level curve will be like this. So this way we see that we can have level curves. Okay, so now the fact that gradient points in this direction, so I can visualize this here, right? So it will be like in this direction gradient increases. So I have to go here, and then that way I can draw it in a 2D plane, and I can study the optimization method, how it's proceeding step by step. Okay, so this is the main idea about gradient level curves. If you see this function here, then level curves look quite interesting because there is a minima here, and then because as the function has a lot of bumps and so on, irregular bumps, then level curves will be also kind of irregular. So here, if you see, this is the minima of this function. So here also this is the minima here. Okay, basically here this corresponds to here. So you have several level curves. So basically, looking at the level curve, I can more or less guess that there is some local minima here, there is some local minima or maxima. It could be either, because just level curve doesn't tell me whether it's maxima or minima. Also, I need the heat map, right? So if this is like red, then it's like a maxima, and if these are like green, then maybe it's minima, and so on. So level curves are just a way to visualize algorithms. So when you're writing paper, working on papers on optimization methods, then sometimes often you discuss your arguments by drawing some level curve. Okay, if it's possible to do so, then you do that. And things can get really interesting. For example, just look at this nasty function here. This is taken as a snapshot of a slice of some higher dimensional functions, a slice of some higher dimensional function. So basically, by higher dimensional, I mean it could have been 100 dimensional. So function could have gone from, let us say, 100 to real. Okay, so I can take some slice. Let us say the third dimension and the 50th dimension. So then I will get a slice for that, and then even for that slice, if I plot and take other values constant, then you will see that it's so bad, right? The level curves look so irregular, right? So this type of level curve already tells us how difficult it will be to find maxima or minima of this function, right? So now we understand level curves. So one important thing that I'm not going to prove, usually I prove in the class here, but I leave this in the interest of time. So gradient points in the direction perpendicular to the tangent drawn to the level curve. So now that we know level curves, then one more fact that is interesting is that we know that gradient of f points in the direction of the increase of the function. Okay, so what we also know from calculus is that if I draw level curve, and let us say this is the point, if I draw a tangent to this, then perpendicular to this tangent will be the gradient. Okay, so this helps now. So wherever, let us say I start from here, I want to optimize the function. By optimize, I mean I want to find maximum or minimum of the function. So I have to start from somewhere, because I have no idea where is maximum minima, obviously, because it's a very high dimensional function. So I have to start from somewhere, random point. Okay, and then I need to know where the gradient is pointing, because gradient tells me where the function will increase, and the negative gradient tells me where the function will decrease. Depending on problem is about maximizing a function or minimizing a function, I will take the choice of gradient or minus of the negative of the gradient. So I will draw level curves, and then I will be here. So that will be my x naught, and then I will draw a tangent, and then perpendicular to this will be the gradient. So this will be the increased direction. Then I will go negative gradient. Then I will arrive here. Here also there will be some level curve. It is not drawn, let us say, some level curve, and then I will draw a tangent here, and then perpendicular to this, I will go here. I will reach somewhere here, let us say. Again, I will draw a tangent, then perpendicular to this, or let us say the negative of the gradient I am interested in. Positive was this way. Then I go negative of the gradient. Then I reach here, and then there will be another level curve here. So this way I can proceed. So basically on I have many level curves. I start from some initial guess, and then I draw the tangent, and then I perpendicular of that gives me the gradient, and then go to the negative gradient and so on, and then I keep doing this until certain point. Then I will get at local minima. How do I stop? Well, I will stop where the grade f becomes tends to 0, because at minima necessarily the function minima or maxima, the function has to go to 0, right? So for example, if I see here, then definitely the gradient must become 0, right? The tangent is flat, right? So all local minima, the tangent should go to 0, minima or maxima, right? So these are the critical points of the function. So I will stop wherever I am, either here or either here or either here. Of course, you can say that you didn't reach to the global, but gradient method doesn't take you to the global. Gradient method only guarantees local. So once the gradient becomes flat, you don't know what to do. Okay, so you will be stuck there, and you will report this as the solution. Okay, so we will come back to this later. So one can prove this result, that the tangent to the level curve will be perpendicular to the gradient. So proof also requires the knowledge of implicit function theorem from advanced calculus. The implicit function theorem is needed in the sense that what we want is that locally I should be able to express each of these curves as some function of x or y, and that is needed in the proof of the proof of the fact that gradient points perpendicular to the direction of the level curve. So I'm not going to do the proof, but I'm just telling you that some requirements are there in the proof, which, for example, is implicit function theorem. And if you are from a maths student background, then these things you already know by now. What is an implicit function theorem? Well, and what exactly is implicit function theorem? Basically, it says that some functions can be written only implicitly. Like this circle equation can be written implicitly. You cannot express one x as a function of y or one y as a function of x, and that will not be a function. What do I mean by that? For example, x square plus y square is equal to 5. So if I solve for y square, right? So y square is 5 minus x square, and y will be plus minus square root of 5 minus x square, right? So this is like a function is in two parts, right? And this is not a well-defined function. Why is that? Because it is upper hemisphere combined with lower hemisphere, right? So upper hemisphere combined with lower hemisphere. This is not a function. Why is that? Because at one point it's taking two values, right? So at one point it's taking two values, right? This and this, and that violates function, right? So this is not a function, right? Not a function. So what happens is that equation of a circle, from equation of the circle, you cannot express y as a function of x and such that it is a function. Okay, same thing you can say for x. So x will be plus minus square root of 5 minus y square. So again, this is not a function. Okay, if you take only half, then it's a function. If you take only other half, then it's a function, because for one input you have one output. But if you take both, then it's not a function. Okay, so the point here for the implicit function theorem is that it says that, okay, if you cannot express your x and y globally, but then if you can express it locally. So let us say locally, by locally I mean, let us say this part. So in this part, let us say, can you express x as a function of y? Then it is clear, because for this part, for this part, I can indeed express this part in term with this output. Okay, so locally I can do that, not globally, because globally, if I see, let us say this part, then it's not a function, because for one input I have to output and so on. Okay, so locally I will be able to express function express one x as a function of y and so on. Okay, so this is what is implicit function theorem, and if you can do that, then this result will be useful in the proof of implicit function theorem. For example, the proof is also very simple. So suppose fxy is equal to c is the level curve. Then by implicit function theorem, even if the level curve is a circle, by implicit function theorem, I can write this into small parts such that y can be expressed as a function of x. And so in that area, that part, I can substitute y is equal to yx in f. So f x y yx is c. Then I apply the derivative, and from there I get the slope value, and the tangent vector to the level curve will be given by, we know that is del f by del x, so del f by del y. So this we know, and this we have computed. So if you take the dot product of this, then we will see that since grad f is this, and this one. So the tangent that is going through the level curve is this vector. If I take a dot product of this with this, then it goes to 0. Okay, I'll leave this up to you to verify later on. I will leave the slides for you. I'm skipping the proofs part because I have to cover many things, but this is elementary. I leave this as an exercise. Check this. Okay, so basically this is the from here you get the tangent vector, and now you check that the gradient of f is perpendicular to the tangent vector. Okay, so now coming back, why I have already told you now motivation of y gradients, because gradients, or let us say the negative of the gradient, gives you direction of descent. In other words, the direction you have to go to decrease the function value. So the motivation is clear. And level curve, why are we using level curve? We are using level curve to do analysis on 2D basically on paper or something, because we cannot plot 3D functions and so on, and it's hard to visualize. So we can do the same analysis on 2D. Okay. Where does the gradient point to? I have already said gradient points the direction of increase, and negative will be in the point of instantaneous decrease. So how does the gradient happen going to minima? We have also answered this question, because we can follow negative gradient step by step to go to the minima. Okay, so then we can write an algorithm now. So what is the algorithm? Algorithm says that initial guess you have to choose, because you don't know where to start. This is an iterative algorithm. Right, so we don't know where to start. So let us say we start from x node. Then from the current position, which in your case is x node, x0. So you have to move in the direction of negative grad f. The negative grad f should be computed at x node. So this you can compute. Now you will update the new position as xi plus 1 will be xi minus gradient fxi. And you are taking t step in that direction. Okay, so t happens to be a parameter that tells me, okay, I know the direction, which is negative grad f xi, but how far I have to go? Let us say t length you have to go in that direction. Okay, and when to stop? Well, you can stop when the gradient of f goes to 0, or let us say in machine precision, in double precision, it could be, let us say, less than 10 to the minus 16. then you would like to stop the algorithm, right? So because if it is close to zero, then you will see that there will be no update, because this will be zero, then xi plus one will be just xi only. Okay, so basically gradient method will not work, and you have to essentially stop when gradient f is goes to zero. Okay, so that's the point here. Okay, or another way to check is that the change in the xi value, because if gradient is becoming flat, that also means that xi plus one is very close to xi. Okay, so hence the difference will be small. So once you get to this stopping criteria, then you can report the last xi to be the minima. Okay, so this is an algorithm that helps you to find minima of f of x over x. This is the problem. This algorithm will help you to find. Of course, I understand that this is a very basic algorithm, but you will be surprised to know that this is the basic idea that is used in machine learning in a slightly different way, and those are the things I will explain to you today. What variations of these are used in large scale machine learning, but the main workhorse of solving such problems are actually gradient descent method. Okay, now a quiz question would be, what should be changed to find maxima? So this algorithm that I told you is for minima, right? So this is for minima. Now, what should I do to find a maxima, right? So
you have to change to plus sign.
yes, we have to change this to plus, right? And just to add a little bit, of course, most of you have understood this by now. Just to recall your vector algebra, right? Vector algebra says what? Let us say someone gives you xi, right? And someone tells you that, oh, look, if you go in that direction, you are basically asking for directions, right? So this is your current direction, position, which is also a vector, right? And then someone tells you, you go in that direction, right? So someone tells me, go in that direction, which is minus negative grad f(x), to minimize the function, right? So what do? This itself is a vector, right? Let us say all vectors are have tail at origin, and someone tells you this direction, right? So you move this parallel, right? And you go this direction, right? This is how vector algebra works, right? And your new position becomes now this, right? So this is vector addition and nothing else, right? So if you are someone who works with vector, then this is what you're trying to do, right? So current position vector plus the direction that you want to go, it will be your new position, which is xi plus 1. The only thing is, like, no one is telling you for the moment how far, right? And that's when you get this parameter t. Okay, because so then this becomes a hyperparameter, and this is something you have to figure out. So how direction you know, but you don't know the length, how far you want to go in that direction, right? And this is an important thing because, and it also happens that we don't know in practice. Okay, so hence we call such parameters hyperparameters. So parameters that you can't estimate, parameters that are not fixed in advance. Okay, so let me write it like this. So this is, you will see a lot in if you read machine learning papers. So parameters that are not fixed, that are not fixed in advance, right? So these are the parameters you need to explore a little bit on your own. Okay, so this is something we don't know. Why we don't know? We don't know because let us say my function is like this, right? So what might happen is that, let us say I'm my starting pointer was here, because I don't know, because it's a very bad function, very high dimensional. So I have no idea where I should be starting, because ideally I should start very close to the minima or somewhere like that, but I have no idea. So I will start randomly. So this will be x0. Now let us say it says that direction of decrease is this, right? So gradient increase is this. So I will go to the negative. So this will be decrease, right? So I will go this, right? But I don't know how far, right? So let us say I went let us say I went this far, okay, or let us say let me do some other. Yeah, let us say I did this far, okay. So from X I went this far, right? So by doing that, I did not improve my chance because I did a T. Direction was okay, but I did too much because I arrived at somewhere here, which was not a good decrease, and also I missed the global minima. I mean, that is not the point anyway, because that also I don't have control. But what is happening here is that I did too much and I arrived at something where it is still a very high value. And if I had taken T to be, let us say I was modest and I would have taken T to be just this much, then I would have been here, which is now very close to minima. And then I would have taken T small again, I would have reached to the minima, right? So taking T is not an easy thing, okay? Taking too high would mean that even though you may have been close to local minimum, now you are not sure where you are. If you are lucky, then you may arrive at even better minima. You never know. That's why we call it hyperparameter, right? Because if the function, let us say I modify this function to be like this, then let us say you choose T high without like knowing too much. So then you arrive here. So maybe you did better actually. You arrived at a even better local minima now. But then if you choose T very large, although you are close to local minima, you have no concrete idea what exactly is local minima. Like how far it will go down, you don't know. So you may be greedy and say, oh, okay, maybe I should take more because in your mind it could be that maybe the function is like this. So you may be greedy and want to choose this much, but ideally you should have chosen this much. Okay, so that's why it's like hyperparameter. We don't know. You may be lucky and then you choose this T and you arrive at close to this, but then now you have to decrease your T very, very small. Otherwise, you're going to miss this. But the problem is you don't know. You don't know that this will be this minima, or this will be this minima, or this will be this minima. So you should have taken T large also so that you could have gone quickly. The point here of T choosing large is that you are greedy to choose T large enough so that you are going quickly to the minima, right? Because if you keep taking, let us say the function is like this, right? And you are so afraid that you keep taking T small because you think, oh, I don't want to take risk. I want to. So it's like life, right? You in life, sometimes some people take small risk, right? So they say, oh, okay, I don't want to do this. I don't want to invest too much money. I want to be safe. So you will go like this slowly. Okay. So you will be rich, but by then you will be very old. Okay. So, but then if someone is greedy, then they might invest a lot. And maybe in one shot they get here, okay, which is what they want, maybe, okay. But then again, it's a risk. Just it's a risk, and doing too much might make it worse, like I have explained it here. Okay, so that's why it's called hyperparameter. We don't know this T. So there are many heuristics to choose T, basically. Okay, so and there is no one can suggest you what is the best T. Okay, this itself is a research problem. Research problem for given problem, because in general you don't know. But if the function has some characteristics, okay, let us say function has some structure, then it might help you to get an estimate of a good T. Okay? That's the point here. But in general, it's itself a open research problem on how to find suitable T's. Okay. What could be the way? Maybe you can take higher order derivative, maybe higher order derivative, like second derivative, third derivative, because so far we have used first derivative, right? But second derivative might tell more, right? Third derivative might tell, but those are costly also, right? So that could be line of research where you may want to make use of those things, second derivative and so on. Okay, but there are trade-offs. Second derivative is very costly. Okay. So as you said, if I want to maximize, then I will just change -2 plus here. That's only one change I have to do. All other stopping criteria, everything remains same, because the gradient will become flat also at maxima and also at minima. So technically, stopping criteria, if I am doing maximization problem, again I have to stop at maxima because tangent will become flat, meaning a gradient will be 0, or minima also the stopping criteria is same, because again the gradient will become flat and norm will be, or gradient will be 0. So everything remains same. It's just that instead of minus you have a plus here. Okay, so for which function, now one of the question is for which functions we can guarantee that gradient descent is guaranteed to find maximum minima. Certainly not for this, right? Because it all depends on the starting point. So if I start here, I go here, then I arrive at maxima, right? But then it could be that this was the better maxima, right? So it did not guarantee. It guaranteed only local maxima, right? It did not guarantee the global minimum. So now the question is, what is it in the function that is preventing you from finding the global minima? Basically, the problem is with this lot of jumps, right? So if it has only one jump, then it was guaranteed, because there is only one, so it will go definitely to this. For example, this is fine, right? This is also fine, right? And this is also fine, right? This is also fine, right? So you can see the shape of the function. If they are like this, then it is guaranteed, right? Because no matter where I start, it will keep doing like this, right? It will keep going like this. And since there is only one local minima, it will stop here. And since there is only one minima, it has to stop here. There is no, I mean, there is no other local minima which is smaller, right? So same thing is going here, right? So if I go here, then I go here, and then I arrive at some minima, right? Similarly here in this case, if I go here and then go here and then go here, and I arrive at a local minima. So what do we conclude from here? The function should be a ball shaped, right? So any cups, ball. Let us say ball is because cups are not necessarily all like this, right? Some stylish cups are like can be like this. We don't know. We have never seen cups like this, but let us say balls are always like this, right? So ball shape. Okay, so mathematicians define such functions. Okay, they call such functions as convex functions. Okay, so these are convex functions. So convex functions guarantee that gradient descent will converge to global minima, because there is only one minima, and there is no problem of getting stuck or in some local and not reaching, because there is only one. So getting stuck is exactly the one I'm looking for anyway, right? So there is only one minima. In those cases, those are actually the convex function. And in those cases, basically, the gradient method is guaranteed to work. Okay, so then they have developed concrete examples of how do you define such functions. For example, someone gives me a complicated function, okay, and then how do I define convex? Because ball shape could be also in higher dimension, right? So here I can maybe visualize, but let us say if I give you a function like this, x, y is x square plus y square. Now, can you tell me it's ball shape? Or let us say if I do even higher dimension, x, y, z, then x square plus y square plus z square. So can you plot like you may not be able to, because this is 4D function, right? So it's not always easy for you to plot and tell me, oh no, sir, it's looking like a ball shape. You can't do this, right? Because it's 4D function, right? So we can't do this. So we need a way to check, right? We need a way to check convexity in higher dimensions. So that's why it's important to define what exactly is convexity. And sometimes things are even more, sometimes it could be a function of a matrix. Okay, so sometimes we deal with functions like this. F of A is trace of A. Okay, now how will you tell me this is a ball shape or something? This is a very high dimension. So this is a function of a matrix, but yet it can be convex function. Okay, so that's why we need a concrete definition so that it can be applied in higher dimensions or even abstractly in some matrix, or sometimes some of my student works with tensor. So it could be a tensor function. So as a tensor variable, is it convex? Okay, so we want to define. So before we define a convex function, we will define something called convex set. So there are two things, convex set and convex functions. Okay, their definitions are different. So we should not confuse with convex set and convex function. So first we will define convex set. So convex set is a set in which every line between 2 points stays in the set. So if you see this, let us say this one, and let me remove this one. So let us say this one. Then every 2 points in the, so let us say I took 2 points. If I draw the line joining them, then all the points of the line is inside, completely inside. Okay, so take another 2 points. Okay, and line joining them. Okay, here. So all the points on the line joining is completely inside. So if you do this for all points, any arbitrary points, and if the line joining 2 points is always completely inside the set, then it's called convex set. Now, mathematically, how do we do this? Well, we need to understand how to represent a line joining 2 points. So basically, we want to know how to represent a line segment given 2 points. So given 2 points x1, x2, right? How do I generate the points between these 2 points, right? So the way to do is theta times x1 plus 1 minus theta times x2. So this is called parametric equation of a line. Parametric equation of line between x1 and x2, right? So how is that? And theta goes from 0 to 1. So let us say theta equals to 0, right? If theta equals to 0, then what do I get? X2, right? So basically at theta equals to 0, we are at x2, and theta equals to 1, we are at x1. And if you vary theta continuously between 0 and 1, let us say you take theta to be half. Theta to be half will be the midpoint, because theta half would mean x1 plus x2 by 2. We know that this is the midpoint between x1 and x2. Between x1 and x2. Okay, this is a midpoint between x1 and x2. And with this intuition, you can say that if you choose some theta, then it will be this value. It's theta if you choose this value. So theta must be between 0 and 1. That's how you ensure that these are only the points between and not outside. Okay, if you take theta greater than 1, then you will get some points outside that. So that should be allowed. Okay, so this gives you a line joining 2 points, and then the idea is that a set C is convex if this point is in C. Okay, all the points for all theta values, all the points between x1 and x2 is in C. If that is the case, then it's called a convex set. One can also define general convex combination. So this is also called convex combination. So in linear algebra, you may have seen linear combination alpha 1 plus alpha 2 x2. So this recall it's called a linear combination, right? So, but in linear combination, there is no restriction on alpha 1, alpha 2, right? So alpha 1, alpha 2 is taken to be any real number, right? So no restriction on alpha 1, alpha 2. But compared to that, here you can say this is alpha 1 x1, so this is alpha 2 x2, where alpha 1 is theta and alpha 2 is 1 minus theta. But here you will see that there is a restriction on alpha 1 and alpha 2, right? Basically alpha 2 is 1 minus alpha 1, and they must be lying between 0 and 1. And that is the reason why you only generate points between two points, and you don't do anything. Whereas if you do take a linear combination, then it will be like all the points. So if I take a linear combination, then linear combination will be everything. Also extends beyond x1 and x2. So this is linear combination. Okay, and this part is convex combination, right? Convex restricts between 2 points, right? So yeah, so we understand the convex combination. So these were studied by first proposed in some German mathematician. So this text is in German. So that's okay. One second. One second. Let me see. Okay, so I have like half an hour. Okay, so we have seen convex sets, and Oh, okay. So it seems that I have missed one slide here. So convex function. Okay, so convex function, I will define it right here. Okay, so a function f from let us say, yeah, any set a to b is convex if um, so the way convex function is defined, remember I gave you an intuition that convex function should look like a ball shape, right? So how do I characterize this? I characterize this by saying that if it is indeed a ball shape, then one property is good. What can you say about this? The points joining on this line, these two points taken on the curve, is always above the curve. And it is interesting to see that this characterizes a convex function. Because if it is a ball shape, then this property should hold for any 2 points. So let us say I took 2 points, line joining this. So this you should not confuse with convex set. Convex, I'm not talking about convex set now. Now I'm talking about convex function. So the definition is slightly different. So a function is convex if I take any 2 points on the function curve, and the line joining the 2 points on the points on the function curve is always above the function values on the curve. Okay, it's always above the function values on the curve. Now this is what we need to write it mathematically, right? So points joining 2 points. So let us say x1 and x2, right? x1 and x2 are the 2 points. Then the function values will be so line joining these two will be so this is fx1, right? And this is fx2 function value, right? The line joining this I have to now write, right? So what will be the line joining this? Well, it will be the same way like in the set. So t of f of x1 plus 1 minus t of f of x2, and this gives me the line joining the 2 points, and this must be above. This means it should be greater than equal to the function values on the curve, right? So function values on the curve are this. So this means I should put the function values the function values here, right? So these 2 points, right? x1 and x2. So I need to consider now these lines and then apply f on this to get function values on the curve. So this will be tx1 plus 1 minus tx2, right? So this is how I define convex function. Okay, so so we can test a few things, right? For example, let us say fx is x square is convex function or not, right? So you may want to prove this, right, using let us say the line definition. So let us say you take take arbitrary points x1, x2, and then you have to show that t times fx1 plus 1 minus t times fx2 is greater than equal to f of t times x1 plus 1 minus t times x2, right? So you may do the, let us say, the left hand side. It may not be like very simple to prove this, but just to tell you that these are the things you may have to do. So let us say t times fx1. x1 is x1 square plus 1 minus t. x2 square is greater than equal to f of t of x1 plus 1. So this is t x1 plus 1 minus t x2 and this whole square. So does this inequality hold, right? If you prove this, then you can say that for any x and y, x1 and x2 in the domain of f, if you prove this, then you prove that this is a convex function. Okay, then you can prove that this is a convex function. So what you see here is that in this case, this happens to be a differentiable function, right? Because I can take the derivative, right? So if you can take the derivative of function, there are some easier ways to prove convexity. So this inequality may not be very easy to prove, but since the fact that this is a differentiable function, right? So this is differentiable. So this means this fact can be used to use some simpler notions of convexity. For example, there is something called first order convexity, which is shown here. Okay, so first order convexity tells us that suppose the function f is differentiable, then the function f is convex if and only if domain of f is convex. That's also needed. And so the domain of f is a convex set. Let us be very clear, okay? Domain is a set. So we are talking about set convexity. And here when I say f is convex, then I'm talking about function convexity. So set convexity means any 2 points line joining them is completely inside. Whereas function convexity means the line joining 2 points on the curve is above the function values between those 2 points. Okay, there is a slight difference here. Okay, so if the function is differentiable, domain of f is convex, then convexity can be guaranteed by this. Okay, the convexity can be guaranteed by this. So maybe for the example we considered, let us say fx is x square. So can we try this on this, right? So according to this, what would be the grad f? So since this is a single value, so grad f is just derivative, which is 2x. So if I can prove this, okay. So what is fy? So fy is y square. So is y square greater than equal to fx is, let us say, x square plus grad fx, which is 2x times and y minus x. Okay. So does this hold for all x and y in the domain of f? So domain of f happens to be all of R. So for all x comma y in domain of f, in this case it's all of R. Okay. So we may want to prove this inequality, which may be a bit simpler. So let us simplify a little bit. So x square plus 2xy, and this is minus 2x square, right? So this is minus 2x square. So this becomes minus x square, right? So 2xy and minus x square. So is y square greater than equal to 2xy minus x square? What do you think? Is y square always greater than equal to 2xy minus x square? Right? That's the question. If we can show that, then we can claim that this is a convex function using first order condition. Right? So what do we think? Is it always true? Right? What if I take this on the left hand side, right? So this is y square plus x square minus 2xy. Is this greater than equal to 0? Right? So what do you think? Is this greater than equal to 0 all the time? So I can simplify this, right? It seems to be square of something, right? If it is square of something, then it will be greater than equal to 0. So this is nothing but x minus y whole square, right? And this is indeed greater than equal to 0. This is true because this is square of any number is greater than equal to 0, right? So this implies f is convex using first order condition, right? So this was a little bit simpler compared to what you see here. This may not be that simple to prove. This is the first definition of convexity, line definitions, right? This seems to be slightly complicated, although we have to see actually how complicated it could be. But this seemed pretty straightforward to prove, right? So first order convexity can be applied when function is differentiable. Why it is called first order convex? Because you are using first derivative. So that's why it's called first order condition. Now you can also ask, is there second order? Yes, there is also second order condition. And second order condition is even more simpler. It says you take one more derivative, grad fx, and if it is positive definite, because if you take one more derivative, then it will become a matrix. So if the matrix is positive definite, then it will be greater than 0. In this case, double derivative won't be a matrix because it's a real variable function. So if I take one more derivative, so f double prime of x is just 2, which is greater than 0. So that also tells me that it's positive definite. Implies if f is convex. So this is a second derivative. This is second derivative test. So there is something called second order condition, which means that this is the second order condition. Okay. So convexity, now you learn three different ways, right? So there is a line definition of convexity, which is defined here. So this is the first definition. This is the second definition of convexity, but second definition requires function to be differentiable so that you can take the derivative. And the third is this condition where the second derivative is positive or or positive definite. So there are some geometrical interpretation of this. Basically, it says that this which acts like a tangent, this one is acts like a global underestimator. Basically, if you do a tangent, then all function values lie on one side of the plane, right? And this is true for convex function. So no matter where I go, I drew a plane. The function values are always on one side. Okay, so that's the geometrical view of first order convexity. Now, if you look closely, then if you look closely, then you will see that this is a Taylor approximation of the function f. I mean, this is a Taylor approximation of the Taylor series. If you remember, Taylor approximation of f at x. Okay, so these are two terms of the Taylor series. Okay, that's why I call it approximation. So what exactly is the Taylor's? What happened? Another way to say is that convex function, the first two terms of the Taylor approximation acts as a global underestimator. Okay, it's like it acts as a global lower bound at x. Okay, so global lower bound at x, global lower bound at x. Okay, so that acts as a global lower bound. So that's another way to say, if someone asks you what is a first order condition, then you can say the first two terms of the Taylor approximation acts as a global lower bound. If that happens for all x, at any x I do the Taylor expansion, take first two terms, and it happens to be a lower bound, then the function must be called a convex function. So this is the second order condition that I just told you. In the second order condition, also now we have to assume we need twice differentiable, because in the condition I need twice derivative, right? So there are functions which are differentiable once but not twice. For example, x mod x. Okay, differentiable once but not twice. Okay. So there are functions where you may not be able to apply second order conditions. Okay, so you may have to work with, let us say, first order condition only. Okay, but if the function is second order derivative, for example, x square, so second derivative is also well defined, then I can apply the second order condition. So it's much easier now, because f prime x was 2x and f double prime x was 2, and it's greater than 0. Done. It's like just two lines proof, and I can immediately declare that it's a convex function. Okay, but if it is a higher dimensional function, for example, if it goes from, let us say, R2 to R, and let us say I give you the function xy is x square plus y square, then I have to compute first gradient and then one more gradient of the gradient, right? So let us see in this example what will happen. So grad f, if I do, so grad f, how it is defined? Del f by del x, partial derivative, del f by del y. So if I do del f by del x, I get 2x, and then this is 2y. And if I take one more, right? So if I take grad square fx, right? So let me create some space here. So let us say I take grad square fx. Grad square fx is what? Del 2f by del x square, del 2f by del x del y, del 2f by del y del x, and del 2f by del y square, right? So this is how the second derivative is. So what is that? So del 2f by del x square. So del f by del x I already have. So I take one more derivative with respect to x, so I will get 2. Now del f by del y I already have, and I have to do del by del x of del f by del y. So del f by del y is this. I have to do del by del x. But if I do del by del x, because there is no x, this will be treated as a constant. Hence, this will be 0. Similarly, this will be 0, and this will be 2. Now, the question, the definition tells you that the grad square f must be positive definite. So this stands for positive definite. Positive definite. Okay. So this means that you have to prove that this matrix is positive definite. But this is positive definite. Because you see on the diagonal I have 2, and these are the eigenvalues, and eigenvalues are positive, right? So basically it's easy to say that it's positive definite. What is the definition of positive definite? A matrix A is positive definite. A is positive definite or symmetric positive definite if x transpose Ex is greater than equal to 0 for all x not equal to 0. This is what we know for positive definiteness, right? So this definition can be applied here also. Why is that? Let us say x1, x2, and then we have 2, 0, 0, 2, and then x1, x2. Then what do I have from here? So this is 2x1 square plus 2x2 square, right? And this is a positive quantity, right? Because x1 square and x2 square are positive. So this is indeed a positive definite. Okay. So we have seen an example of second order condition and how it can be used in a twice differentiable function. This is a twice differentiable function and how we can use it to prove that it's a convex function. So now I can claim using second order derivative that this function is a convex function. Okay, so convexity can be defined. For example, if you want to consider an example here, then let us say you are given a function this, where P, Q, and R are given, then you can use second order derivative, right? So if you use the second order, so if you do the first derivative of this, if you do first derivative of this, then what will you get? You will get Px plus Q. P is a matrix here. Q is a vector. Okay, so you need a little bit of practice on finding derivatives and so on, but you can try this as an exercise of how to compute derivative. But in this case, I will say first derivative, I get Px plus Q. And if I do one more, then I will just get P. So second derivative is P. So basically, this function will be convex if P is positive definite. So it's convex if P is positive definite. Okay. So everything depends on P now. Q and R has no role here. Q and R, you can take anything. But as long as you keep P to be positive definite, this whole function is going to be convex. And once it is convex, you can apply gradient descent method, and it is guaranteed to converge to local minima. Okay, that's the point here. We are studying convexity just to make sure that we identify all those nice problems which are convex. It could be very high dimensional, and we cannot visualize, but at least if we can prove, then we are sure that a gradient descent method is going to converge for such problems. So what is important is that you cannot remove the fact that domain of F is convex. So it's an important part. You can say that why are we asking for domain of F to be convex? If you see here, then F is convex if we are requiring domain of F to be convex, right? So why is this requirement? So there is an example where that will tell you why this is needed. For example, if you see this, then what is this function? Fx is 1 by s square, right? So if I plot this function, right? So fx is 1 by x square is this, and is this, right? So this is the function, right? In the domain x is not equal to 0. So basically this is removed from the domain, right? This is removed from the domain. This is removed from the domain. So this is the function, right? Now the question is, you see the domain is convex or not? First question is that, right? Is domain convex here, right? So whole line, but you have just removed one point, right? So what do you think? Is the domain convex function a convex set, right? Is domain convex set? Right? So what do you think? Anyone? So what do you think? Is this a convex set? Okay, so no answer. Why is that? Why can't you answer this? So you have 1 point removed, right? From a line, right? yeah, it can't be convex, right? So this is not a convex set. Why is that? Well, it's not a convex set because I take 2 points, join the line, then the point in the middle is removed, right? So that point won't be in the set. So that will make it non-convex, right? Okay. So this is not a convex set, right? So this is not a convex set, but what implication it has? So uh, so so the fact that you have removed this, okay, and it satisfies the second order condition nicely for all points in the domain. So if you see this part for all x in the domain, it satisfies second order condition, which is f dot prime x greater than 0. And similarly, for all points here, it satisfies the second order condition. But it is not a convex function, okay? Because the domain was not convex. And why is that? Because I can take 2 points, let us say here, okay, and here. Then what does the convex function definition says? The convex function definition says that the points on the line joining 2 points on the curve must be uh, above the curve values. But then these curve values are here. Okay, the line is below actually. So this violates the definition of convexity. Okay, so that's the problem here. Okay, so that's why it's not a convex function. So domain of the function should be convex. Okay, to make a guarantee that overall it will be a convex function. Okay, now you can take this as an exercise to prove that how whether these functions are convex. Exponential of e to the x, x to the a, x to the b, log x, and all this. You may try this. So basically, you can use second order condition, first order condition, or the line definitions, and so on. Now I will move to um, some interesting models, or let us say some interesting functions, which are prominent in data science and machine learning. These are called neural networks. So now I will focus on how optimization method can be used in these special type of functions. Okay, so let us see let us first see what are these neural network functions, and then we will see what are the problems people face. And the reason why we are interested in neural network function is that it's now everywhere. For example, image recognition, image generation, speech recognition. So the speech recognition used by Siri or the Google Voice in your mobile phone, or even the directions that are told to you. All this uses in some sense some neural network. It could also be the language translation. For example, if you use Google Translate to translate English to Hindi or so on, then again it is done using neural network. So neural network has become very important now. Neural network is also used to solve science problems now. For example, differential equations can be solved also using neural networks. So there are wide-ranging applications, and the use of this area is going to explode in future. It is being used to now predict protein folding in biosciences, to detect let us say X-ray images. Sometimes it's doing better than persons. Okay, so it's now being used more and more. So that's why it's became very important, and hence the problem of finding the maxima or minima of functions in these area is becoming a very important area to consider, because it has a lot of impact. So that's why, in that spirit, I will introduce you to neural networks. Okay, so my goal is also to introduce you to neural network, and then come back to tell you how optimization method will be used there. Okay, so to start with neural network, the first thing would be to tell you the basic unit of neural network. The basic unit of neural network is called perceptron. Okay, so perceptron, what it means is that you will get some input. Let us say this is the input you have. Okay, and you do a linear combination of the input. So let us say you do x1 w1, and then you do plus x2w2 plus x3w3 plus dot 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 plus xn wn. You did a linear combination. So this denotes the linear combination sigma. Okay. And after that, you do some kind of thresholding. So you say that if sigma is greater than some value, let us say threshold t, then output let us say 0, and if sigma else output 1. Okay. Now, what is that threshold and what could be the condition? These are like secondary thing, but this is how the overall function is. Okay. It takes the input x1 xn, it does some linear combination, and it does some final check. And if the check satisfies something, it produces 0, it produces 1. So whole thing, you can see this as a function. Okay. The whole thing, you can see this as a function. Okay. So remarks are that the number of inputs combined linearly. So that's what I explained to you just now. The threshold is the fire if combined input exceeds some threshold. So this is the threshold that you define. So for example, linear combination xi minus t is greater than 0. So this is the t is the threshold, or otherwise you produce 0. Okay. So in this case, you are producing Boolean output 1 or 0. So when this was proposed and its use was shown in some cases. So I will come to that in detail now in a couple of minutes. But yeah, 1 second, just to check the time. So 10:30. Sorry, 11:30 is 12:30 and 1:30. Okay, well, I do have time. Okay, sorry. So I was thinking, so I have like 40 minutes more. Okay, that's very good. So then in that I will explain neural networks to a large extent. So the building block is a perceptron, and its use was shown in some in 1958. Its use was shown in some small examples, and even with that example, people were quite impressed, and they were so impressed that if you see the New York Times, which is the prominent newspaper in US, then when it was discovered, they said originally assumed could represent any Boolean circuit. So they thought that it can represent Boolean circuit. I will come back to that. So as you know, in computer science, you have gates, right? So you have like a OR gate or AND gate or JOR gate and so on, right? So these are the basic building units of building blocks of doing computing, right? So you're doing logical operations. So combining this, okay, NOT gate and so on, combining this, you can create any kind of logical operations. So they're like fully, logically complete set of operations, right? So logically complete. What are the logically complete operators? For example, if I do and NOT, then using this, I can create any logical program, basically. Okay, or I could have taken OR. Let's say OR is denoted like this, and NOT. So this is also logically complete. Okay, and then there are NAND gate, NAND, NOR. Okay, not of AND, and then not of OR, and so on. So. So these gates themselves, NAND gate themselves alone is like functionally complete. So I can like create AND or using just NAND gate and not using NAND gate and so on. So what I'm trying to say is that if you can, by any means of computation, if you can produce effect of an AND gate and NOT gate, okay, AND gate and NOT gate, then using this you can create any logic. Okay, that's one point. And if you can create any logic, then you can build a computer system based on that, because it will be able to do any kind of computing, right? So the point here is that when they proposed the perceptron framework, then when they proposed the perceptron, then they showed that it can do these operations, which is done by classical gates like AND and or NOT and so on. So when they did that, then people were excited. They said that okay, if that is the case, then it will be so powerful that it will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Okay, so maybe these were too far-fetched at that time, but uh, what we see now is actually it's happening. So now you will see many uh, of the I mean, there are agents that can, for example, there are news readers, AI based news readers. They can give a news reading. Okay, and those are like based on they are trained using neural networks. For example, C. So for example, as I said, you give an image of let us say cat, dog, persons, and so on. Now there are neural network based architectures that can recognize that this is the person, this is the cat, this is a building, and so on. So in some sense, they are able to see. It's able to write. So there are neural network based architectures. For example, NLP using some of the architectures such as LSTM, RNN. Okay, these are all neural network based architecture. They are built. They are used. They are built using these as basic ingredient. Okay, so RNN transformer. Okay, and so on. Basically, it keeps coming. Okay, so new architecture keeps coming. So so these are the architectures with which you can start writing. So there are agents, for example, in GPT-3, you can search in Google, search in YouTube, search in YouTube. And I don't have much time, so you can search in YouTube to see how GPT-3 can be used to write write a story, poetry, news article. Okay, so it can write, it can generate a new story. I'm not talking about story from the past, that will be copying, right? It will generate a new essay, new poetry. Okay, so that is becoming that powerful. So sometimes it's the poetry that it writes is better than what most of us can write. Okay, it can write LaTeX. Okay, from it can generate LaTeX documents. So quite a few thing it can do. So basically, it can write to large extent. Of course, these things are in improvement, but in 10 years from now, they will be so powerful that they will be doing things perhaps better than humans. And that is why the people are in people are in a danger a little bit now, because they think that that AI can take the jobs of usual people. For example, a person who is working in a radiology department who takes X-ray images and points out the disease or whatever you're looking at the X-ray image. Now those things are better done by a software. Okay, so it is 99% or something like that accurate, and human beings can be only 85% accurate or so on. So it's better, it's doing better than humans. So radio someone who is in radiology department, he will lose the job. Okay, so similarly, if you do self-driving car and so on, now since it is able to see now, although it is not perfect, it is able to see, so it can decide when to stop. What is the, if car is coming from the other side, and which lane it has to follow. It can identify tree and so on. It can identify traffic light. When traffic light is green, it can start the car and continue. It can control the handle of the car. So that's why you can also search autonomous driving in YouTube. Okay, because I don't have time to motivate you, but the point here is that the reason why most of the research is focusing on now optimization method from maths point of view on neural network is because it's being used a lot. Okay, it's used a lot, and in next upcoming year, it's going to even become more and more important. So that is the reason why, from research point of view, these areas are hot. And if you do something here, you have a better chance of getting a recognition, and usefulness of your idea can be well recognized. Okay, so with this motivation, so let me now go into a little bit of detail. So. So the important thing that I have to tell you is the following. So first of all, why? I mean, what is all this going on in this function? I see wi, I see xi, I do some threshold. Like what exactly is going on? Like why are we doing this, right? So if you so to give a motivation to you, I need to show you a little bit of regression model. I don't have a slide, but I will quickly show you what machine learning is trying to do, okay, as a basic thing. So let us say machine learning is all about pattern recognition. Okay, so that's, let us be very fixed about that. It's about pattern recognition. Any problem where you want to do a pattern recognition. So for example, it could be somebody's voice. So you want to understand the voice. So that's like you want to find a pattern in the voice. So that's pattern recognition. Okay. Or sometimes people call it perception. So any problem that involves perception, like, so perception is based on our senses. So for example, how we see. So it's like visual perception. How we hear, that's our sound perception. Okay. So all this kind of problem where we want to understand the pattern, okay, pattern in the image, and from their pattern we recognize it's a cat, dog, or whatever. Okay, similarly we identify pattern in the signal of the voice that we signal that we receive. So that's also pattern. Okay, so overall all these algorithms in machine learning are all about pattern recognition. Okay, so if so it's all about pattern recognition. So now the question is it possible to understand the pattern after some practice? Right, and if I can understand that, then it is called learning, right? So because I learned from my experience and then I got better. Okay, so for example, let us say if I have a child, right? So child, do you think child knows everything in the start in from the beginning? Not really, right? So child learns about many things like gravity. Okay, so child, if it is very newborn, then they don't know gravity. Okay, so they don't know gravity. For example, if a child is very newborn, let us say just 3 or 4 months old, and if you show to the child that the ball is there, and then it drops to the ground. Okay, so this is the concept of gravity, right? So child may not be impressed by this, because child has no idea that there is a law that tells that ball, if it is released, then it will go down only. But if so let us say this is 6 month child, right? But then if you go to 1 year child, okay, I'm not completely sure when, but let us say maybe 1 year, and then let us say if the ball is here, and let us say if the ball goes, if you release the ball and if it ball goes up, okay, then child will be surprised. Child will be surprised. Why the child is surprised? Child is surprised because it seems that it's violating something. It seems that the child has learned something from 6 months, so learned gravity. The child has learned gravity along the way, because it has seen all the time that someone, when is really something really, it goes down. Okay, the leaves of the tree they go down. Anything that is released, that goes down. So during these months, child learned that this is the rule, and he or she must assume this rule. But anything in the after all these observations, if you release a ball, it goes up, child will be extremely surprised and sometimes even afraid that this is not what he has seen, right? So what child has learned is not obeying what he has learned, right? And the question is, what happened when it went from 6 months to 1 year, right? Learning happened, right? So many things in the world are happening via learning, and we are assuming those rules along the way. Many things like that, right? We are assuming those rules along the way, and this is, in some sense, we are doing machine learning. The child is doing some kind of machine learning. There are some parameters in child's mind or something that is getting reinforced when they see each time these rules, and then they assume that things will, if it is released, it will fall. So hence they will be afraid to jump from the bed, because they know that they will fall. And one more thing, there are many other things they learn in the process, right? For example, let us say the child first time touches a a hot, let us say plate or something like that, okay, or a cup or something like that, okay. So then when they touch, then it's so hot that they get the sensory senses in their hand, and then it and the body gives them a reward, and then it's a pain, and then next time the child sees a cup, and let us say some vapor is coming from the cup, and maybe there is a flame and a stove and so on. So child, if you see a 6-month child, they will touch it because they don't know that it's hot, right? But then if they touch it once, if they touch it one more time, let us say sometime there was something in the plate, some vegetable or something is there. Let us say something is there, and then also the some vapor was coming, and then also child touched another time, and then they said, okay, it is also hot because they get the senses in their hand that okay, it's hot. So child is learning along the process. Child was not told in the beginning that things like this are hot. So in some sense, child is also doing machine learning by looking at the situations and thinking that okay, if there is a fire, it's supposed to be hot. If there is a vapor coming out, it's supposed to be hot. And this could be also in a plate. This could also be in some other cases. So what child is learning is the main points of features of what makes it hot. So this is child is understanding the pattern, right? So the pattern is like maybe vapor is a very strong pattern of something being hot. Fire is something being hot, right? So so machine so machine learning is trying to do the same thing. So machine learning is trying to learn like a child. Okay, it's trying to see things. It's trying to interpret things which could be hot or so on. And for the moment, machine learning is not doing this sensory things of hot and something, but it is trying to see and understand. Okay, it's trying to hear and understand. So all these things are perception based. Now the question is, if child is learning, then what is being, I mean, what could be the let us say, what could be the way to make something learn, right? So what we believe is that if the child has some template in their mind, okay, so they have a brain, and then there is some template is there in their mind. So template, by template I mean template function is there in their mind, and that have certain number of weights. Okay, some weights, and these are there. But when the child sees something like this, these template function weights get updated. So the next time it sees this, it knows for sure that this is going to be hot. Okay, the first time it sees it, the weight gets updated a little bit, and the body gives the reward that it's hot. And let us say it's like it's not very reinforced right now because it was the first time. But then it sees that again there is some other scenario where there is a vapor. In this case, there was a fire as well. But there in the case there is a vapor. So this vapor again, when the child touches this, the brain, there is some initial weights. Those weights get reinforced again. Then the brain is learning that saying, okay, I'm improving my model, and if it is there is a vapor, it is surely again going to be hot. So this prediction ability of the mind is improving each time the child is experiencing new things. Okay, so in the abstract sense, what is happening is that in the child's mind there is a template function. Template function. This template function has some free weights parameters, and it is open to receive inputs. So this could be the vector x. This vector x goes in. Okay, and this gets through some template function which has some free parameter weights. These weights gets updated each time to do a better prediction. Okay, so it keeps doing, so it learns each time. So new x will come, and then looking at that, weights will modify again, and it will become better in prediction. So more or less machine learning is all about this, that there will be a template function with free parameters, and each time you will get a new x and you will improve your learning method. Okay, so that's kind of machine learning for you. So if I want to illustrate this with a small example, let us say in chemistry, people do this line fitting and so on, right? So let us say in chemistry they get this data. Okay, so they did some ingredient was there. They based on that ingredient, if they chemistry or anything, any scientific area, they had some input and then they got some output. They get some input, some got output. Now they want to understand the pattern in the data. Okay, because they could collect it only for some samples, right? Because they cannot do it for infinitely many. So from this small enough sample they want to predict, right? It could be, for example, very simple thing as time of the day and then the temperature that you get, right? So let us say at 8 a.m. the temperature is, let us say, 18 degrees Celsius. At 9 a.m. it's 30 degrees Celsius, and so on, right? So these are the values that you have calculated. Now I want to learn the pattern in my function, right? So I want to learn the pattern. So pattern could be like something like this. Okay, assuming that it doesn't get suddenly hot or suddenly cold. So I believe that the pattern is like this. So basically it means that I want to fit a function through these points. Now, if I learn this function, then next time someone may ask, okay, predict what is the temperature there. Although this was not used during fitting. Now, once I have found the pattern, then I can say, okay, if this is the case, then perhaps this should be the temperature. Okay, because I know the function now, I can say that, right? So this is exactly what machine learning tries to do. Given a lot of experience, it finds a function that fits through those points. Once it fits, then it can see some other scenario. For example, in the child case, it saw a cup, right? And it saw a plate. Okay. Now it could be something else. It could be glass, right? And still the vapor is coming out, right? So maybe the cup is this observation, plate is this observation, glass can be somewhere here. So it is, a child is trying to interpolate. Okay, it is not cup, it is not plate, it is glass, but I know something is, it is looking like hot only because it's somewhere in the middle, because it's also vapor is coming out. So it could be some intermediate place here. So that's how child will say, okay, this is also in the hot category. Okay, so that's how so machine learning is all about interpolation. It's based on the given samples, you identify the pattern. And once you identify the pattern, then some intermediate situation comes in your life, then you can make some calculated guess that it is where it may lie. Right? So now the question is, how do I fit a function like this, right? So for example, in this simple case, what I can do is the following. So what I can do is that, so let us say this is a point x1, x2, x3, x4, right? So at x1, I get the output, let us say some output, let us say y1, x2, I get the output y2, and so on. And xn, I get the output yn, right? Now I want to fit the function through this. So I will choose some template function. So choose template function, choose template function. So in this case, let us say I want to use, let us say third degree polynomial, let us say. So for example, I choose the function as ax cube plus bx square plus cx plus c. So this is the template I decide in advance. So I will say that I want to choose like this, but I have not fit it yet. I have to move this in a nice way so that it pass through this. But at least the template there, based on A, B, C, and D, I will find out. These points will be, the curve will be passing close to the points or through the points. So now the requirement is, so this is the template I choose in advance. Okay. And then I will say that, okay, now f at x1 must be y1. So this means that ax1 cube plus bx1 square plus cx1 is d, a plus d is equal to y1. That's what I want. Ax2 cube plus b x2 square plus c x2 plus d is y2. So I write the equations for n points, right? Axn cube plus b xn square plus c xn plus d is yn. Okay, so so now I have to solve for a b c d, right? So I will make this as a matrix x1 cube x1 square, x1 1, x2 cube, x2 square, x2 1, and so on, xn cube, xn square, xn 1. So this is my matrix, and the unknown is a, b, c, d, because knowing a, b, c, d will tell me the exact curve, right? And the output is y1, y2, yn. So I can solve this using linear algebra. So solve this using linear algebra. And if I solve this, then I get ABCD. Once I get ABCD, then my function is learned. Then basically I have learned how to go close to these points. And once I have known this, then I have kind of got the pattern. Now, if a new data comes, I can just look at the learned function and then I will project it upward and say, okay, this could be the predicted answer. Okay, so this is more or less what machine learning tries to do, but machine learning tries to use complicated template functions. That's only the difference. In this problem, regression problem, we have used this cubic polynomial, but machine learning will do very complicated nested functions. Okay, so let us now, with this motivation, let us see what kind of template function neural networks are. Okay, so we started with perceptron. So perceptron is a template because if you see perceptron, then wi's are the unknowns in the function that I would like to estimate the weights of my function. Just like A, B, C, D in the model for temperature prediction. Now here W1, W2, Wn are the weights which I want to learn. Okay, so these are the weights I want to learn. So this will be the motivation. So earlier, when perceptron was invented, they said that perceptron can be used to act like an AND gate, okay, or it could be used to act like a NOT gate and OR gate. And in these simple cases, you can actually predict the correct weight so that it will act like an AND gate. For example, X, Y, and X and Y. So if we recall the AND, so 1, 1 is 1, 1, 0 is 0, right? So 0, 1 is 0 and 0, 0 is 0, right? So this is the AND operation. So now let us check this, right? So let us say first case 1, 1 goes inside, right? So 1 times 1, 1 times 1, so linear combination of this, plus 1 times 1, plus 1 times 1. Is this greater than the threshold, greater than or equal to the threshold, right? So this is greater than or equal to 2. In this case, yes. Hence the output will be 1. Right, because this is greater than threshold. That's how I define the threshold. Now check other case 1, 0, right? So 1 times 1 plus, and now it is 0, right? And so 1 and 0, we are talking about this now. So 0 times 1. Now this is 1. Is this greater than or equal to 2? No. So the output is 0, which is what we want, right? So you can check for other two cases that it is indeed working like an AND gate. What is interesting is that we have fixed the weight here. So there was no real learning, so to say, because we already knew what weight was. Learning part is how you learn the weights, right? But in this case, it was easy to just guess. But what is important is that this perceptron is acting like an AND gate, which I told you before. If you can produce AND gate and NOT gate, you can create logic, right? By combining these in certain way. You can also create other logic like or NAND or NOR and so on. Okay. Similarly, if you see this perceptron, it's acting like a NOT gate. Okay. So if I take anything this 1 and since this is -1, it will always make it negative. Hence, it will be not of this. Right? So you have to define the threshold in a correct way, and then it will produce the NOT. So 1, it should be 0, and 0, it should be 1, because 0 times -1 will be 0, and then you say greater than 0 will be yeah. So if it is so if it is 1, then 1 times -1 is -1, and -1 is less than 0, so it will produce 0. And if it is 0, then it will be 0, so it will be less than or equal to 0, then it will produce 1. So basically how you define threshold, you can produce the NOT operation. Similarly, you can produce the OR operation with this. So basically, if you can generate this, then the idea was that then it can be used to generate any other get. But soon they encountered something is that they cannot use JOR. For example, which weights you will choose here So this is exclusive OR. Okay. So which weights you will choose here, okay, and the corresponding threshold such that it will act like a Shor. But the fact is that actually it won't be possible for a perceptron to create Jor. But is this not a contradiction that I told you that since it does this, it can produce any logic operation? Yes, it can do that, but not by just one perceptron. You should be able to combine to produce this. So that's what is possible. So for example, here, if I combine perceptrons like this, if I can combine perceptrons like this, then it is able to produce Jor operation. So I leave this as an exercise to you. So this is exercise for you to check that this indeed is Jor operation. So here again, I have like identified the correct weights so that it acts like a Jor operation. But important thing was just one perceptron was not enough to create Jor. I needed multiple of the perceptrons to create Jor operation. Okay, so point is that you may be able to create arbitrary kind of logic, for example, this kind of logic, and not of X and of Z or something like that, by combining perceptrons multiple times and so on. So what I'm trying to say, it's possible. It's just that you have to now consider multi-layer perceptron. It's first layer, second layer, third layer, right? So you have to combine perceptron in multiple ways to create arbitrary logic. Okay, one more thing is that when the perceptron was started, it was only working with Boolean. For example, if you see these gates, it's always taking 1 or 0 values, but there is nothing to stop us from taking it real values also. So it can be extended from Boolean to real. So it can take Boolean values, and hence we arrive at this perceptron that we have started with in the beginning. So basically, it can take real inputs x1 to xn. Okay, so it could be inputs could be, let us say, image, right? So image of a cat, let us say some cat is there. Okay, some cat is there, right? And this cat can be represented as a pixel value, right? So RGB, red, green, blue, and different values of red, green, blue can give you these point color images. And based on this, so this image can be represented as a vector of so basically red, green, blue matrix, red, green, blue matrix, and these matrix can be like arranged in a certain way, and you can make it into a vector and so on. So once you do that, you feed this vector. This vector goes in, and then based on the weights and so on, it will try to identify whether it's a cat or not, right? So this input could be language, right? The sentence, right? So let us say I ate today. So you can do character by character vector encoding of this. So I is denoted by some vector, A is denoted by some vector, T is denoted by some vector, right? So you once you make a vector, you concatenate maybe, and then put it there, and then this will be an input for you. So input could be in many ways. It could be signal, voice signal. You write it as a vector, and it can go there, right? So it could be many things. So here is again the same perceptron, but instead of the threshold, I can also use some threshold. Threshold is like a not differentiable function, because threshold is like either greater than or equal to t, then something, or else it is something. So this creates a discontinuity. The function, the threshold function would look like this. So if you want a continuous function that acts like a threshold, then it could be sigmoid, which acts like this. Okay. So if the function is here, then you say this. If the function is on this part of the value, then you produce this output. So there is no sharp corner. So it stays differentiable. So differentiability is good. As I said in the beginning, if you want to do gradient descent, then we would like to be able to differentiate this function. So if the threshold function is differentiable, it will help. Okay, so MLP can be used to do some arbitrary classification problem. For example, one problem is, can you build a learning algorithm that can identify whether the point is inside this yellow region or outside? Right? So we can do that. In this case, is that we need perceptrons. So one perceptron can act like a to identify one boundary. Another perceptron can act like to identify another boundary, another perceptron to another boundary, another perceptron to another boundary, and so on. So I will need perceptron 1, 2, 3, 4, 5. I will need 5 perceptrons to identify whether the point is inside or not. How I will know that? So this perceptron will tell me the point is on this side, basically this side. Okay, and this perceptron will tell me, oh, indeed the point is on this side. Okay, and this perceptron will tell me the point is on this side. This perceptron will tell me point is on this side, and so on. So if all the 5 tells that point is on the correct side, then if I do an AND of this, and if it turns out to be 1, then we can classify that we can say that point is in the yellow region. Right. So perceptron can be used. So for example, let us say this is how we are building a perceptron. Okay. So let us say I want to learn this one. So I need a 1 perceptron. Okay. And if I want to learn this boundary, I will add 1 more perceptron. So basically, second boundary I need second perceptron. First boundary I will need first perceptron. Second boundary I need second perceptron. To learn this boundary I need a third perceptron. And then a 4th perceptron, 5th perceptron, and so on. So now I can build a multi-layer perceptron. So so now I can also do some complicated tasks. For example, point could be here or here. Okay. So for this, I will need 5 perceptron. For this, I will need 5 perceptron. So 1, 2, 3, 4, 5 to say whether the point is this side, point is this side, or point is this side, point is this side, and so on. But I also have 1 more now. So again, I have to do 1 more. So 1, 2, 3, 4, 5 sides. And this will tell me whether the point is inside this pentagon. And I have to do, because the point could be either or this, right? So first I have to check whether this is inside. So I will do AND of this. So whether the point is inside here, and I will do AND of this to identify the point is inside here. And then I will do OR of this, because the point could be either here or here. So then I do OR. And then that will be the final output. Okay. So perceptron can be used to learn complicated decision boundaries, and it could be very complicated because the point is inside it or not, right? So we may need a lot more complicated. Perceptrons can be used, for example, let us say to identify whether a digit is 2 or not. Okay. So again, this is a black and white. So this will be just one matrix where it will tell me the intensity of points. So for example, this pixel denotes 1 point. This pixel denotes 1 point. Other points are white. So like this. So this way it's a matrix, but then I can make it into a vector. If I make it into a vector, then this vector will go inside, and then the weights are there. These weights will be updated using optimization method, because these are level data. So for example, if I do this, then I know for sure that the output is 2. So let us say initially the weights are not known, then this goes in, and initially the weights will be random because I don't know, and then it will produce something. Let us say some y tilde. Then I will check with 2. Okay. So if I check with 2, and so basically I will build a loss function from here to here. So the function value times subtract, and then what is the actual level. Let us say this actual level is y. Then the optimization problem is to minimize this. Now x is known. What is there is w, right? So w. So I want to minimize. I want to find the weight of my function, adjust my weight of my function such that f of x comma w, x is known during training because x is this pixel values. So it is not far from the given level, which is 2, because during training data, it is known, it is given to me that for this image, there is a 2, for another image, it is 3. So this is called training data. So I will keep doing this, just like in the weather prediction model. I had some samples in hand, say that at this time the temperature was this, at this time temperature was this, at this time temperature was this. So some sample was given, and based on that, I found a pattern, right? So same thing is happening here. I will be given many handwritten digit data, and corresponding label will be given. And just like here, time temperature was given, here it is given to us that it is 2 or not, or something like that. So based on this, we will We will take a difference to measure how different it are. So I will tune the weights W. My goal is to minimize. So whatever output I got, it should be close enough to 2. So I want to minimize the output, which is fxw from y. So if I can do that, if I can do that, then I have learned the weight. So if I do this for many samples, then my model will learn. My model will tune the weights in such a way that next time something like this, slightly different from this comes, it will know how to say whether it is true or not. Just like here, if something new comes, then it learns to show, okay, this is close to maybe this temperature, okay, so slightly higher maybe. So something like this happens here also. When a new data comes, then it learns to start predicting how close. So it will say predictions. So maybe, oh, it is like 90% 2. So then you will say, okay, let us assume 2 only, right? So that's how it is. It's all about prediction, right? So this is how machine learning works. You have perceptron. From perceptron, you build a complicated perceptrons which include many layer and so on. And then this becomes a template function. Just like in the here, you have a ax cube and so on. So there you have template function where the weights were a, b, c, d. Here now your weights are inside this, like this. And then you optimize this. So that's where optimization function, optimization method is needed. Okay, so these things can be used, as I said, for image text captioning and image. Let us say you upload some pictures on Facebook, and maybe Facebook can automatically identify the captions of you and your friend and so on. It could be used to play games, for example, chess game. Maybe the agent can play a game on its own. Maybe given a voice signal, it can do the transcription, so voice to text translation and so on. Behind all this, now neural networks are used. That is why it's become important. So one thing now we need to understand is that since this is a template function, like I explained here, now we would like to use the gradient method, right? So now our function that we want to minimize, I can take this as a loss function, right? Loss function is f xw minus y. Now this is a minimization over L. So now we know that to minimize, we can use gradient descent method. So we need to know how to compute the gradient, right? So we need to know how to compute the gradient, and how do you compute gradient of this nested function? So that becomes an important part, which I will also explain in the next part of the talk. So that's why understanding how the gradient method works is important. And here chain rule will be needed to understand the how to take the gradient, right? So this is an example of computing the gradient in a single MLP. So for example, if I want to what gradients I want to compute? I want to compute gradients with respect to the weights, right? So, but then since it is a chain type of function, so this takes this takes this takes this. So that's why we need to use the chain rule to go from here to here, to go from here to here, and then finally arrive at the gradient with respect to the weights. So gradient. So first we will do dy by dz, dy by z, right? So we go like this. So we go like this, dy by dz, because y is a function of z, and y is a function of z in the sense that y is sigma z. So dy by dz is sigma prime z. Now z is this guy, right? So z is wyxi. So I want dy by dw. So dy by dw by dy by dz, and z is a function of w. So hence by chain rule, I can write dz by dw. So that's why it is being done here. dy by dz. Now dy by dz you already have, and then dz by dw. Now dz by dw, if you see, if I take derivative of z with w, then only xi will be left, right? So that's why you get sigma prime z xi. So these are the things we need in gradient descent, right? Because we need these gradient values, right? And this is why we need to know how chain rule can be applied to compute the derivative with respect to the weights. So that's the idea here, and that's basically the basically slightly more detailed view of neural networks. So some input goes in, I multiply with the weights. So this whole weights can be assembled as a matrix. Okay, so then these outputs are nothing but linear combination of the weights. A2 is a linear combination of the weights again. A3 is a linear combination of the weights. So all this can be visualized as a matrix form. Okay, and then A1 output, which is like these can be written as W1 transpose A naught plus B1, and then you arrive at some other layer. So next layer, if you go there, then you do some activation of the output. So let us say A11, then I do G of A11. Similarly, when I do linear combination, I do activation, which is called G of A12. And then G of N. So this is some kind of activation function. Okay. So then the next step is H, which is H11, H12, H13 vector, is a G of output A11, A12, A13, which is A1 here. So you do this again you do the linear combination here, and then you get A21, A22, A23, and then you do the activation like this, and then you get H is G of A2. So I have written in matrix and vector for compactness. So overall function is can be written like this. So overall function, if you see, it looks like this. It's a nested function. Okay, so that's where the difficulty lies. It's a nested function. Okay, so I will stop here in the first part, and we will continue with this in the next part, where I will show you how to take derivative in this complicated case. Okay, then. Thanks for your attention.
Okay, thank you.
Yep. See you.
See you in 2:30.
At 2:30. Okay. Yeah. Thanks. Okay. Bye.